Hello students, welcome. I am Selvan from Unique Chemistry. In this presentation, I am going to explain the basic concept of term symbol and its importance. So it is a simple and clear explanation for deriving ground state term symbol for transition metal ions. As you know that electron has two types of motion. It is spinning in its own axis and revolving around the nucleus. It is well known fact that a charged particle and revolution will generate magnetic field. So as an electron has both spinning and orbital rotation, it produces two different magnetic fields. They are referred as spin angular momentum and orbital angular momentum. It is common phenomena that two magnetic fields, when they are very close to each other, cannot go independently. They tend to interact or couple with each other. If only one electron present in an orbital, then the interaction is simple as it is only between spin and orbital motion of same electron. But if more than one electron present, there may be greater interaction which leads to more splitting in electronic energy levels. It is important to note that the completely filled orbital or completely empty orbitals will have no resultant magnetic momentum value. Both spin and orbital momentum will be zero. So the alkali metal ions or alkaline metal ions will be magnetically inert since they have completely filled orbitals in their excited ionic state. The same is true for inert gases. But in the case of d-block transition metal ions, they exhibit multiple valency with the multiple oxidation state. They have partly filled orbitals even in the highest excited state. This leads extensive magnetic interaction between electrons in the case of transition metals. So it is noteworthy to describe about the electronic energy states in presence of magnetic interactions by the empirical notation known as term symbol, especially for transition metal ions. So now we understand how we define the term symbol. One or more electrons in an orbital can be arranged in number of ways, and energy differences arising from different electronic repulsions and different orbital angular momenta for these various electronic arrangements assigned with term symbols. So for example, if one electron is present in the d orbitals, that electron can be placed in dxy or dyz or dxz or dx squared minus y squared or dz squared. So the 5 arrangement of one electron in the d orbital, so there are 5 degenerate energy state for that one electron. So now we see what is meant by coupling of angular momenta. An electron has both spin angular momentum and orbital angular momentum. Already we have seen. Both of these motions produces magnetic field perpendicular to the plane of rotations. Each electron can be considered as very small bar magnet. So it's just as a magnet. So what will happen? Because if you keep two magnets very near to each other, what will happen? The first magnetic field will interact with the magnetic field of other magnet and vice versa. So just like that, the electron is a magnet and he has two types of magnetic moment, and more than one electron is present, what will happen? The whole magnetic field of first electrons, the spin and orbital angular momentum, that's a magnetic field of first electron, and the same things in the second electron will interact, so you will have more number of interactions. So these interactions leads to splitting of energy levels. The coupling of angular momenta can be recorded as coupling between two vectors A and B to produce resultant vector C. So we can represent this angular momentum, spin or orbital angular momentum in vector representations. So now see, there are two figures are given in this diagram. The first one is the precession of A and B around C. The A represents one angular momentum and B represents another angular momentum. Both will couple with each other to give the resultant angular momentum around C. The same is denoted in another form where A and B gives a resultant vector in C. Now we see what is meant by RUSSEL-SAUNDERS or LS coupling. The spin of one electron can interact in 3 ways. For example, if one electron is there, it has a spin angular momentum. Then this spin angular moment or momentum will interact in 3 different ways. First, with the spin of the other electron. If more than one electron is present, the spin of first electron will interact with the spin of second electron. And the orbital of the first electron will interact with the spin of electron will interact with the orbital of the same electron. Then third, the spin of the first electron will interact with the orbital of the second electron. But actually the third interaction is very, very smaller in contribution and is neglected. The resultant angular momentum is expressed in units of h by 2 pi. Now we see the types of coupling. There are three types of coupling. One is a spin-spin coupling, orbit-orbit coupling, and a spin-orbit coupling. The spin-spinning coupling is a coupling between two electrons. If more than one electron is present, as an example, if two electrons are present, the spin of first electron will couple with the spin of second electron. So it is known as the spin-spin coupling. Now the total spin quantum number for the two electrons is represented as the capital S is equal to small s1 plus s2, s1 plus s2 minus 1, s1 plus s2 minus 2, up to s1 minus s2. The bracket, this type of bracket indicates the absolute value irrespective of sign. The next one is the orbit-orbit coupling. The total orbital angular momentum is denoted as the capital L is equal to small L1 plus L2, L1 plus L2 minus 1, L1 plus L2 minus 2, up to L1 minus L2. The third one is spin-orbit coupling. Now, there is an extensive coupling between resultant orbital and resultant spin angular momentum. This is known as LS coupling or Russell-Saunders coupling. It is recorded as capital J is equal to capital L plus capital S. Then L plus S minus 1, L plus S minus 2, up to L minus S. So, these are all the three different coupling in the angular momentum, that is a spin angular momentum and the orbital angular momentum. So the coupling taking place among the electrons, if more than one electrons present, or two electrons or three electrons, many electron systems, the coupling is taking place as the number of electrons is increased. Now the term letters. So this is very important because the term symbol is represented by the term letter. How do you assign term letter? Actually, the total or resultant orbital angular momentum L is assigned a term letter according to the value of L. So, which value possessed by L, the letter is a different letter is assigned. For example, if L is 0, then it is a capital S. If L is 1, it is a capital P. If L is 2, then it is capital D. If L is 3, then capital F. If L is equal to 4, then capital G. If L is 5, the capital H. So, according to the value of L, this letter must be assigned. Next one is a very important one is the spin multiplicity. Actually, the spin multiplicity is presented at the left corner, top corner of the term symbol. The spin multiplicity describes the number of possible projections of a resultant spin quantum number S in presence of a magnetic field. So, the MS, that is a spin magnetic moment value will be given as S minus 1 up to minus S. As an example, when S equal to 1, it implies that the value of spin multiplicity is ms equal to 1, 0, minus 1, a triplet. Thus, the spin multiplicity is defined as 2s plus 1. If s equal to 1, the spin multiplicity will be 3, since 2 into 1 plus 1 is equal to 3. So, now the ms equal to 1, 0, minus 1, a triplet. Now, there are three ms values are given for s equal to 1 configurations. Here, the positive value 1 refers to the z component of the angular momentum aligned with the field parallel. So, it go along with the field. The 0 represents the alignment in perpendicular directions. The negative value, the minus 1, denotes opposing the field, that is anti-parallel. So, the spin multiplicity is indicated by a superscript at the upper left of the term symbol. It is important to note that a completely filled orbitals contribute nothing to L or S, since the sum of ms and ml will be 0. For example, in the d orbital having all 10 electrons, the L value will be 0, because the left hand side 2 into 2, 4, 2 into 1, 2, and 0 into 2, 0. Here minus 1 into 2, minus 2, here minus 2 into 2, minus 4. So, totally the sum of all these ml values will be equal to 0. And also with respect to the spin, all are paired electrons. So, they are paired electrons So in each orbital there are 2 electrons in opposite directions. So the net resultant or net spin is 0. So totally the S value is also 0. Now we see how do you assign term symbols. Actually there are some important rules we have to adopt. The spectroscopic term symbols for transition metal ion at ground state. The following rules are adopted to assign the term symbols. The first rule says that the electron prefers to retain parallel spin as long as possible. That means the first electron will go to the first orbital, then second electron will go to the second orbital only, not the pairing is taking place. So this is a Hund's rule. So because it retains the parallel spin as long as possible, thus obeying the Hund's rule, it leads to spin multiplicity 2s plus 1, that is a spin multiplicity is maximized. The second rule is the electron prefers to occupy higher positive ML value first. So if for example, if for a p orbital the ML values are plus 1, 0, minus 1, then the first electron will go to the plus 1 orbital, subcell. In the d orbital, the first electron will go to the plus 2 level. So this is the preference. Actually the electron prefers to occupy higher positive ML value first. This will maximize the orbital angular momentum value L. Then the third rule says that the spin orbit quantum number J will have the value according to less than or more than half filled orbital. For example, if the subcell is less than half filled, J is equal to L minus S. If the subcell is half filled or more than half filled, J is equal to L plus S. Now the term symbol is given by the notations. The L, the capital L at the center. The left top corner is a spin multiplicity is given as 2s plus 1, and right bottom corner it is a J, that is a LS coupling, that is a spin orbit quantum number. So now the L must be replaced with the terminal operator. If L is equal to 0, capital S must be placed. If L is equal to 1, capital P is placed. If L is equal to 2, the capital D must be placed in this place of L. So and likewise. The next, we have to see the examples of some transition metal ions with its D configuration, Dn configurations. For example, titanium 3 plus ion. The titanium 3 plus ion is a D1 configuration. How do you find out the Dn configurations for your transition metals? The formula is, it is the atomic number of the transition metal minus 18 is the inert gas configuration minus the oxidation number. So titanium, the atomic number is 22 minus 18 minus 3, you will get 1 electron in the d orbital. This is a d1 configuration. So now the ML values are presented as plus 2, plus 1, 0, minus 1, minus 2. So now as a rule, the first electron go to the highest ML value plus 2. So now L is equal to 2. How do you find out L value? It's nothing but the 1 electron is present, then 1 into the ML value. There is a sum of ML components in subcell. There is a 1 into 2 is equal to 2. So it is D state. So if L is equal to 2, now we replace this L by the capital letter D. And yes, only 1 electron is present and clockwise, so S is equal to half. Now the sum of MS values correspond to the direction of spin. Clockwise spin, it is a plus 1 by 2, plus half, or anti-clockwise it is a minus half. So the spin multiplicity is 2s plus 1, so S is equal to 1 by 2, so 2 into 1 by 2 plus 1 is equal to 2. So this is a 2s plus 1 spin multiplicity. J is equal to L minus S for less than half field. So 2, L is equal to 2, S is equal to half, so 2 minus half is equal to 3 by 2. So the term symbol for D1 system by definition L 2s plus 1 J is given as actually it read as doublet D3 half, doublet D3 half. So this is actual way of reading this term symbol. Then the second example for D2 configurations, examples vanadium 3 plus ion. Now 2 electrons will occupy these ML values, that is subcells, plus 2 and plus 1. So 1 electron in the plus 2 level and another electron in the plus 1 level. So the L is equal to 1 into 2 plus 1 into 1. So 2 plus 1 is a 3. So now it is a F state. Now the L is replaced by the capital letter F. And S, what is S? Because two electrons are both at parallel spin, so 1 by 2 plus 1 by 2 is equal to 1. Then 2s plus 1 is equal to 3, because s is equal to 1, and now the 2s plus 1 is equal to 3. And j is equal to L minus s is equal to 2. So the term symbol triplet F2, triplet F2. And the third example, chromium 3 plus ion and Mn 4 plus ion, there is a D3 configurations. Now 3 electrons occupy the plus 2 level, plus 1 level and 0 level. Now the L is equal to 2 plus 1 plus 0. Now the same 3, that is a F state. And S equal to 3 by 2, because the 3 parallel electrons for each electron is S value is 1 by 2. So 3 into 1 by 2 is 3 by 2. And you substitute the S value in this 2s plus 1 spin multiplicity, you will get 2s plus 1, that is equal to 4. And J is equal to L minus S, that is L is 3 and S is 3 by 2, and 3 minus 3 by 2 you will get once again the 3 by 2. Now the term symbol is quartet F 3 of. Quartet F 3 of. Now the fourth example for D4 configurations, examples chromium 2 plus and manganese 3 plus ions. Now the 4 electrons occupying the plus 2, plus 1, 0 and minus 1 level, this ML level, that now the L value will be equal to 2 plus 1 plus 0 minus 1, that is equal to 2, that is a D state, it is a D state, the L value is replaced by D, capital D. And what about the spin? The total spin value will be 4 parallel electrons for each electron, the S value is 1 by 2, and 4 into 1 by 2 it is a 2. Now the 2s plus 1 value, if you substitute the value of s in this spin multiplied by 2s plus 1, you will get 5. And j is equal to L minus s, that is equal to 2 minus 2, it is 0. So then now the term symbol for this D4 configurations is quintet D naught. Quintet D naught. So the next, the fifth example is for D5 configurations, is a manganese 2 plus ion and Fe3 plus ions. Now the 5 electrons occupy the each of 5 orbitals. There is a plus 2, plus 1, 0, minus 1, minus 2. So now the L is equal to 0, because 2 plus 1 plus 0 minus 1 minus 2. So the L value is 0. Now the term letter is S, capital S. And 5 parallel electrons, so 5 into 1 by 2 is a 5 by 2. And if you substitute in the spin multiplicity 2s plus 1, you will get 2 into 5 by 2 plus 1, you will get 6. And J, that is equal to L plus S. That is L is 0 and S is 5 by 2, you will get the J value 5 by 2. So it is half filled, because of its half filled, now the J is equal to L plus S. So now the term symbol is sextet S 5 of. Sextet S 5 of. Now the sixth example for D6 configurations, examples are given as cobalt 3 plus, Fe2 plus and nickel 4 plus. Now you see after completely half-filled orbitals, now the sixth electron will go to the highest, there is a ML value, there is a plus 2. Now you can easily find out that you neglect all 5 half-filled electrons and only 1 electron now go to the plus 2. So L is equal to 2, 1 into 2 is the easy way to calculate this L. Otherwise you can calculate the ordinary normal way by 2 into 2, 4 and 1 into 1, 1. And 1 into 0, 0, minus 1 into minus 1, minus 1, and 1 into minus 2, minus 2. So you will get 2, that is a L value is a 2, that is a letter D, that is a D state. And S equal to 2, because the first subcell will have both paired electrons. So it is a net spin is 0. So only you have to take into account only the 4 parallel electrons. So 4 into 1 by 2, you will get 2. S equal to 2. Now the 2s plus 1, the value of the spin multiplicity will be equal to the 5, because S equal to 2, 2 into 2 plus 1, 5. And J is equal to more than half fill, so it is L plus S. Now you get L is equal to 2 and S equal to 2, 2 plus 2, you will get 4. So now the term symbol is quintet D4, quintet D4. Okay, the seventh example for D7 configurations, examples cobalt 2 plus, Fe2 plus, and nickel 3 plus. Here once again the 7th electron goes to the plus 1 level, ML level. So only you have to take only these 2 electrons into the consideration. There is a plus 2 level and a plus 1 level, because already 5 electrons are half filled. So this 1 into plus 2 and plus 1 into 1, you will get 3. So now you get, or otherwise you can get 2 into 2, 4, 2 into 1, 2 into 1, 2, 1 into 0, 0, minus 1 into minus 1, 1 into minus 2, you will get 3, the same value you will get. That is a F for 3, else equal to 3, the term letter is F. So S, what about S value? Because the first two subcells are completely, electron are paired, so the spin value is 0. So only the last 3 electrons we take into account. So 3 parallel spins, that is 3 into 1 by 2 is a 3 by 2. So now the spin multiplicity value S equal to 3 by 2, then 2S plus 1 will be equal to 4. And J is equal to L plus S because of more than half filled. And you will get L is equal to 3, S equal to 3 by 2, 3 plus 3 by 2, you will get 9 by 2. So the term symbol is quartet F 9 off. So for D7 configurations is a quartet F 9 off. Another, the 8th example for D8 configurations, example N equal 2 plus. Now you see is electronic, that's ML values are given. Now the L values are 4 plus 2 plus 0 minus 1 minus 2 is equal to 3. The L value is 3, that is the term letter is F. S equal to 1 because only 2 electrons are parallel spin, plus off. So the net is 1. So the 2S plus 1 will be equal to 3 and J is equal to L plus S 4. Now the term symbol is triplet F4. The term symbol for D8 configurations or nickel 2 plus ion, the term symbol is triplet F4. The 9th example for D9 configuration, example copper 2 plus. Now you see this only one electron is left parallel and all electrons are paired. Now this L value is 2 because the last one, the L value is 4 plus 2 plus 0 minus 2 is equal to 2. There is a D state. S is equal to only one unpaired electron is there, so S is equal to 1 by 2. And 2S plus 1, there is a spin multiplicity value is equal to 2 because S is equal to 1 by 2. And the J value is equal to L plus S, that is a L is equal to 2, S is equal to 1 by 2. That's 2 plus 1 by 2 is a 5 by 2. So the term symbol is a doublet D 5 half. Doublet D 5 half. This is the last example for D10 configurations, example copper plus and zinc 2 plus ions. Actually, these both have the completely filled orbitals. So this L is equal to 4 plus 2 plus 0 minus 2 minus 4, there is a 0. So now there is a 0. L is equal to 0. The S term letter is a S state. And the spin value is also equal to 0. That is S is equal to 0 because all are paired electrons. And the 2S plus 1 is equal to 1 because S is equal to 0. You will get only 1. And J is equal to L plus S, that is 0. So now the term symbol is singlet S naught. Singlet S naught. So these are all these are all examples from D1 to D10 configurations with transition metal ions. So many examples are given. And then now you see it is clear from the following table because the one table is given here. DN configurations in the term D0 to D10, D0, D1, D2, D3, D4, D5, D6 up to D10 is given. You see D0 configuration and D10 configuration both are complementary to each other because the maximum 10 electrons in the d orbital. So the complementary configurations for D1 configurations are D9 configurations. For D2 it is a D8. For D4 it is D6. And D5 is somewhat is unique, Now you see one comparison between the D0 and D10. Both are having the same L value and S value. Both L value and S value with respect to L and S, both are same. But if we ignore J is different. So for D0 it is a singlet S naught. For D10 it is a singlet S naught. Both are same. But for D1 it is a doublet D3 half. For D9 it is a doublet D 5 by 2. So if you ignore the J value, the D1 and the complementary configuration D9 both are having the same term symbol with respect to L and S. For D2 it is a triplet F2. For D8 it is a triplet F4. For D4 it is a quintet D0. For D6 it is a quintet D4. For D5 it is a sextet S phi of. Thus, d electrons are very important in deciding the term symbol of transition metals, because this knowledge of term symbol is very essential to understand the spectral properties of transition metal complexes. So now what we have seen is a ground term symbol. So these are the lowest energy term symbols we have derived by using this method. And actually this for every configurations, electronic configurations, apart from the ground term, some other higher terms are also being there that can be determined in some other methods that you will see in the next video. I think this video is helpful for you to understand the term symbol for transition metal ions. So we'll meet in the next video. Thank you for watching.